Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. In this video, we will look at CEF, Cisco Express Forwarding. Historically, Layer 2 forwarding has been much faster than Layer 3, because Layer 2 forwarding is a much simpler process than Layer 3 forwarding. CEF is a method of forwarding packets used by Cisco routers that attempts to bring Layer 3 forwarding speeds up to the level of Layer 2 forwarding speeds. Here's what we'll cover in this video. First, we will review Layer 2 and Layer 3 forwarding. We already covered these topics plenty in this course, so we will just quickly review the necessary information for this video. Then we will look at software-based, hardware-based, and hybrid routers. This refers to what components a router uses to make forwarding decisions. Then we will look at the three main packet forwarding methods used by Cisco routers: process switching, fast switching, and finally the main topic, CEF. And make sure to watch until the end of the video for a bonus practice question from Boson Software's ExSim, my recommended practice exams for ENCOR. Let's get started. To review, Layer 2 forwarding decisions involve looking for an exact match in the MAC address table. Partial matches aren't accepted. In this example, a frame arrives on this switch's F01 interface. It then checks the MAC address table for an exact match, which it finds. It then forwards the frame. It's a fairly simple process, and frames are forwarded as is. By that I mean there is no need to change the source and destination MAC addresses, update the IP time to live, recalculate the frame check sequence, etc. The frame is simply forwarded without changing anything. Because of its relative simplicity, Layer 2 forwarding can more easily be implemented in hardware using ASICs and CAM memory, compared to Layer 3 forwarding. There is usually no need to consult the CPU to make forwarding decisions. And this hardware-based forwarding is much faster than software-based forwarding, in which the CPU is asked to make forwarding decisions. By the way, ASIC stands for Application-Specific Integrated Circuit, a chip customized for a particular use, which is different than the general-purpose CPU, which is designed for more general use. And CAM is Content Addressable Memory, a kind of memory used by switches for rapid lookup of MAC addresses. It allows switches to search the MAC address table in an instant to find a matching entry. Now let's take a look at Layer 3 forwarding. Layer 3 forwarding decisions involve looking for the most specific match in the routing table. Partial matches are okay. Just this alone makes Layer 3 forwarding decisions more complicated than Layer 2. For a Layer 2 forwarding decision, all bits have to match. For Layer 3, only some bits have to match, and the matching route with the most matching bits is selected to forward the packet. So in this example, a packet arrives on the router's G00 interface, and it has to decide what to do with it. It checks the routing table for the most specific matching route. Which one is it in this example? It's this route to 203.0.113.16/28. So the router will forward the packet to the next hop IP address indicated by the route. Note that the router doesn't simply forward the packet like a switch does with a frame. Routers also need to decrement the IP-TTL, recompute the IP header checksum, change the source and destination MAC addresses, and recompute the Ethernet FCS before forwarding a packet. And as a side note, when I say router here, this includes multi-layer switches when they are routing packets. By router, I mean any device performing routing. So the point is that Layer 3 forwarding is more complex than Layer 2 forwarding. Because of this, traditionally, Layer 3 forwarding was done by the CPU, and this made routers much slower than switches, because each message takes more time to process. However, ASICs with TCAM memory allow some Layer 3 forwarding to be done in hardware. CAM memory is binary. It can only use 0 or 1, so it can only search for exact matches. TCAM, ternary content addressable memory, is a kind of memory that does not require an exact match to return a result. It supports 0, 1, and a value called X, which means anything or don't care. This allows for partial matches, such as in the example forwarding decision above. Okay, that's enough review of Layer 2 and Layer 3 forwarding. Now, before looking at the specific packet forwarding methods, let's look at the differences between routers that forward using software and those that forward mainly using hardware. First up, software-based routers. This photo is an ISR 2900 series router. It's a bit of an old model, but it's an example of a software-based router. Software-based routers make forwarding decisions in software using the general-purpose CPU. In these routers, the control and data planes are shared. They are not separate components of the device. Just as a reminder, control plane functions include things like using static routes and dynamic routing protocols like OSPF and BGP to build the routing table. And data plane functions are those directly involved in actually forwarding packets, like looking for the most specific matching route for a specific destination. On these devices, the general-purpose CPU is responsible for all operations. I've seen the general-purpose CPU described as slow and smart. It can't process packets nearly as fast as ASICs designed specifically for that purpose, but it is easily programmable for a variety of purposes, hence the name general-purpose CPU. It offers a trade-off of speed, slower packet processing, for increased flexibility because it is easily programmable. These days, we want to avoid using the general-purpose CPU for forwarding packets whenever possible, because the performance is much worse. So, these routers are generally lower-end routers, compared to the other two types I'll introduce. Next up, hardware-based routers. This router is an ASR 9K series, which is an example of a hardware-based router. These routers make forwarding decisions in purpose-made hardware components. The control and data planes are separate components of the device. The CPU handles the control plane. It's the CPU's responsibility to take all of the information such as configured static routes and routes learned via OSPF, BGP, etc., and create the routing table, as well as to send ARP requests to build the ARP table. Then, ASICs purpose-made for forwarding packets handle the data plane. I've seen them called fast and dumb. They are made for a specific purpose, which they are very good at, but they lack flexibility. You can't program them easily with software like you can with the general-purpose CPU. Now, even in a hardware-based router, not all packets are forwarded by the ASICs. The CPU handles packets that the ASIC can't, and I'll list some examples of such packets later. Aside from software and hardware-based routers, there is a third option: hybrid routers. This photo is an ASR 1K series, an example of a hybrid router. This can be thought of as a middle ground solution between software and hardware-based routers. Like in hardware-based routers, the control and data planes are separate. And once again, the general-purpose CPU handles the control plane. The data plane is handled by a different component, the NP, network processor. So what is an NP? It's a specialized processor for forwarding packets or other network-related functions. These offer a balance of performance and flexibility because they are programmable. However, there are still packets the NP can't handle, in which case the CPU will be used to make a forwarding decision. Here's a chart summarizing these three types of routers. Software-based routers offer relatively low speeds, but are more flexible than the others. Hardware-based routers are the opposite. Their ASICs offer much higher performance, but reduced flexibility. The ASIC hardware has to be purpose-made for forwarding packets. Hybrid routers, using network processors, are a middle ground between the two. Which kind of router is suitable depends on the purpose of the router. But one thing I will repeat is that in modern routers, we want to avoid using the CPU for forwarding packets whenever possible. So, software-based routers, which do all packet forwarding with the general-purpose CPU, are generally lower-end routers, whereas the more expensive high-end routers take advantage of ASICs or network processors for improved performance. Now let's move on to look at the specific methods available for forwarding packets. The first and oldest is process switching. Process switching requires routers to perform a routing table lookup using the CPU for each packet. And by the way, in this case, switching refers to layer 3 forwarding, not layer 2 forwarding by switches. I know it can be confusing, but we sometimes use the term packet switching when referring to the forwarding of packets at layer 3. So you should be aware of the term and not confuse it with what switches do, switching frames. The IP input process on the CPU is responsible for forwarding packets. You can view it with the show processes CPU command. There are a lot of processes running, so you'll have to search a bit through the output or filter the output to find it. Process switching is much slower than CEF, so it should never be used as the primary packet switching method. Keep in mind that it is still used as a fallback method for packets that CEF can't handle, as I'll explain more when we cover CEF. With process switching, for each packet, the CPU must perform a lookup in the routing table and ARP table to forward the packet, and recursive lookups may be required. What do I mean by that? I mean that the CPU won't be able to find the answer with just a single lookup. Here's an example. Let's say the router needs to forward a packet destined for 200.0.0.1. It asks, what is the most specific route for destination 200.0.0.1? A routing table lookup tells R1 that it's the route for 200.0.0.0/24, and that the next hop is 192.168.14.4. It then performs a lookup for the next hop, 192.168.14.4, and learns that the most specific matching route is that to 192.168.4.0/24, and it's directly connected. Because the next hop is directly connected, it checks its ARP table to learn the MAC address of the next hop. Now it has the info it needs to forward the packet. This process of using the CPU to check the contents of the routing table and ARP tables for every single packet is not efficient. Let me demonstrate process switching with this diagram. A packet arrives on an interface of this router. How does it decide what to do next? With process switching, the forwarding decisions of the data plane are done by the general-purpose CPU, so the packet goes to the IP input process running on the CPU. IP input is responsible for doing routing table and ARP table lookups and making the forwarding decision. It does, and the packet is forwarded out of the egress interface. Now, what happens when another packet for the same destination arrives? It once again is sent to IP input, which performs the necessary lookups, and then forwards the packet like the previous one. And what if a third packet to the same destination arrived? The exact same process, sent to IP input, tables checked, forwarding decision made, and packet sent. These days, process switching is used only when necessary, for packets CEF can't handle. However, before CEF was developed, there was one more packet switching method that offered improved performance over process switching. That improved packet switching method was fast switching. Let me demonstrate it. A packet arrives at the router. Just like before, IP input is responsible for doing the necessary routing and ARP table lookups to make the forwarding decision. However, this time that information is stored in a fast switching cache, and the packet is forwarded. Now, in the router's memory, it has stored next hop information for this destination, 203.0.113.20. So, when another packet for that destination arrives, there's no need to do lookups in the routing and ARP tables. The next hop information for that destination is already in memory, so that information is used to forward the packet. And the same thing is done when another packet for that destination arrives. So, fast switching allows the router to build a fast switching cache in memory. To build that cache, the first packet to a destination is process switched, as I showed with the first packet above. Then the next hop info is stored in the cache for quicker lookup next time. For subsequent packets to that same destination, info in the cache is used to make the forwarding decision. Although fast switching did provide performance improvements over process switching, it is generally not used today. I won't read this now, but here's a statement from Cisco. The reason it is no longer supported is because there isn't any reason to use it over the next packet switching method, CEF. Finally, we're on to the main topic of this video. CEF is the default packet switching mechanism for modern Cisco devices. Although it is possible to disable it, there's basically no reason to do that. So what exactly is CEF? First of all, CEF relies on two pre-built caches in the data plane to expedite packet processing. The first is the FIB, Forwarding Information Base. It's built using information in the RIB, Routing Information Base. By the way, RIB is just another name for the routing table. Same thing, different name. In the context of CEF, it's usually called the RIB. The RIB is a control plane construct, built by selecting the best routes from different protocols. The FIB is a data plane construct. It takes the information from the RIB and reconstructs it into simple instructions for how to forward packets. We'll look at the FIB in more detail later. Then, the second cache CEF uses is the Adjacency Table. It's built using information in the ARP table. So, to put it simply, the FIB gives layer 3 information about the next hop, and then the Adjacency Table gives layer 2 information, so the router can add the correct Ethernet header to the packet. Note that CEF is performed on both software-based and hardware-based routers, so you might hear the terms software CEF and hardware CEF. Hybrid routers using network processors use CEF2, of course. That would be considered hardware CEF. In software CEF, the FIB and Adjacency Table are stored in RAM and processed by the CPU. In hardware CEF, the FIB is stored in TCAM, and the Adjacency Table has its own standalone memory, and they are processed by an ASIC, or network processor. Although software CEF doesn't reach hardware forwarding speeds, due to several factors, it achieves much greater speeds than process switching. It's a more efficient way to process packets, whether it's done in software or in hardware ASICs and TCAM. But, of course, hardware CEF provides the best performance. Here's a similar diagram as before, this time for CEF. So, first the FIB and Adjacency Table are pre-built, using info in the routing and ARP tables. Now, building the routing and ARP tables typically involves sending and receiving packets. For example, OSPF packets to build the routing table, and ARP requests and replies to build the ARP table. Those types of messages are handled by the CPU, as in process switching, not by CEF. Now, after the FIB and Adjacency Table are built, they handle the packet forwarding process. CEF allows packets to be switched entirely in the data plane. No need for routing and ARP table lookups. Ideally, CEF will be using ASICs and TCAM, which allows routers to process packets extremely quickly. But as I said before, even in software-based routers, CEF is used. Note that packets which CEF can't handle are punted, meaning they are handled by the IP input process, so they are process switched. Here are some examples of packets which can't be handled by CEF. Packets destined for the router itself. For example, if you ping a router or connect to it with SSH. Also, ACL logging causes packets to be process switched. ACL logging makes the router create syslog messages whenever a packet matches a certain ACL entry, and that requires extra processing. Packets without a layer 2 adjacency. This means there is no entry in the adjacency table, and ARP needs to be done to learn the next hop MAC. And there are other packets which are simply too complex for hardware to handle, such as packets with IP options, which need software processing. Now, CEF is capable of handling a lot of different features, such as QoS, ACLs, NAT, IPsec, GRE, etc. Just know that, although CEF is the default packet switching method, process switching is used as a backup for packets that CEF can't handle. Now let's look at the contents of the FIB. For reference, here is the routing table of this device, so you can compare them if you want. The command to view the FIB is show IPsef. There are 3 columns: prefix, next hop, and interface. Let me just point out a few things about this output. First, if there are multiple routes to a destination in the routing table, that will be reflected in the FIB. I'll briefly mention CEF load balancing in the next slide. In this case, in the routing table 1.1.1.1 and 8.8.8.8, each have 2 routes in the routing table, so there are 2 entries each in the fib. Next, let me point out some values you might find in the next hop column. First, no route. This is used for the default route entry, and it indicates that it's not configured. If you look at the routing table, notice there's no default route, so that's why it says no route in the fib table. Drop means packets to these destinations should be dropped. There are some drop entries in the table that I haven't configured. The first one to 0.0.0.0/8 is for a reserved range. The router normally shouldn't receive packets for this destination. 127.0.0.0/8 is the loopback address range. Again, packets for these destinations shouldn't be traveling over the network. 224.0.0.0/4 is the Class D multicast range. This, by default, drops multicast packets, although notice in the CEF table, there is a more specific route for 224.0.0.0/24, so packets for that specific range won't be dropped. And 240.0.0.0/4 is the Class E range. Again, those are reserved. Okay, next there are receive entries. These packets should be received by the router, not forwarded. For example, the receive next hop is used for IP addresses configured on the router itself, broadcast addresses, among others. And an attached next hop is used for networks directly connected to the router. These entries are like connected routes in the routing table. Okay, so there are some new terms, but overall the fib table is fairly simple. Prefix, next hop, and interface. I used show IP CEF 1.1.1.1/32 to view a specific entry in the fib table. This is one of the entries with 2 next hops, so traffic to 1.1.1.1 will be load balanced. You can add detail to the end of the command to get a bit more information. I've highlighted 2 parts. The epoch is basically a version number for the fib. You don't need to understand its details for ENCOR, I'm just pointing it out here. Notice when I clear the CEF table with clear CEF table IPv4, which causes the table to be cleared and rebuilt, the epoch is incremented by 1. As for the other part I highlighted, per destination is the default load balancing method when there are multiple paths for the same destination. This means that packets for the same source and destination IP pair will always take the same path. It's generally recommended you don't change this, but per packet load balancing can be configured at the interface level. The command is IP load sharing per packet. This means that packets for the same source and destination IP pair can take separate paths. Load balancing is done on a per packet basis. This can have negative effects on some kinds of traffic. That's because it can cause packets to arrive out of order, because they take different paths. So, for example, VoIP traffic can be affected. Really, any UDP traffic is going to have problems with packets arriving out of order. Anyway, here are some more options for the show IP CEF command. There are lots of options that display different info, and also the show CEF command has a variety of options. I recommend experimenting in a lab and checking out some of the different commands available. For now, just remember the basic contents of the fib: destination prefixes, next hops, and interfaces. To summarize the general purpose of the fib, it's used to quickly look up the next hop IP address and the egress interface of packets. It's not so important in this demonstration, but below is the network I'm using to look at the fib and adjacency tables on R1. Now let's look at the other table used by CEF to forward packets, the adjacency table. So, the fib tells the router the next hop, and the adjacency table is used to add the correct Ethernet header to that packet so it can be forwarded. Here's the show adjacency command. It shows the protocol, interface, and IP address, but that's it. This command lists the entries in the adjacency table, but doesn't display the MAC addresses. And by the way, the number in parentheses is the number of internal references to this adjacency. In this case, both entries have 14 references. I doubt you'll be asked about that on the ENCOR exam. I just wanted to point out what it means. So this command is fine if you just want to see what layer 2 adjacencies the router has. But if you want more information, show adjacency detail is better. This command displays more details, including the pre-built Ethernet header that will be used to forward packets to this adjacency. That's the information I've highlighted. It might seem like a random string of characters, but it's not. For example, here's the entry for 192.168.12.2. This string of characters identifies the destination MAC, source MAC, and ether type to be used for frames sent to this adjacency. So the first 12 characters are R2G00's MAC, and next 12 are 1G00's MAC, and the last 4 are 0800, the ether type for IPv4 packets. Then, here is the same information for the adjacency with 192.168.13.3, R3's G00 interface. So, the adjacency table uses information from the ARP table to pre-build the necessary Ethernet headers used to send packets to each next hop. Here's a quick summary of the fib and adjacency table. The fib contains layer 3 next hop information for destination prefixes, and the adjacency table contains layer 2 next hop information. Basically, the adjacency table pre-builds the Ethernet header needed to send packets to the next hop. These two tables together allow for much faster layer 3 forwarding decisions and provide much better performance than process switching, even if CEF is done in software, although hardware is the fastest. Here are the new commands we looked at in this video. The topic of CEF isn't very configuration focused, at least not at the CCNP level. However, I recommend spending some time in the lab, at least getting familiar with the fib and adjacency table, and that's what we'll do in the lab video. Here's what we covered in this video. We reviewed the differences between layer 2 and layer 3 forwarding, and then I introduced software-based, hardware-based, and hybrid routers. Then we looked at the packet switching methods, process switching, fast switching, and finally the main topic, CEF. At the CCIE level, you will have to study more of the intricacies of CEF, but at the CCNP level, you just need to understand the basics of CEF and its components such as the fib and adjacency table. Know that CEF can be implemented both in software using the CPU or in hardware with ASICs or a network processor. Okay, let's go on to the quiz. And watch until the end of the quiz for a bonus question from Boson Software's ExSim, my recommended practice exams for ENCOR. Okay, here's quiz question 1. Which of the following hardware components enables high-speed layer 3 forwarding? Pause the video now to select the best answer. Okay, the answer is TCAM. TCAM, ternary content addressable memory, allows for partial matches, a necessary component of layer 3 forwarding. When using hardware CEF, the fib is stored in TCAM. CAM, on the other hand, does not allow for partial matches, but it is used to enable high-speed layer 2 forwarding in hardware. RAM is used to store tables like the routing table, but RAM does not enable high-speed forwarding like TCAM. And CEF, is not a hardware component, but rather a packet switching method. Okay, let's go to question 2. Process switching is very demanding on which hardware component? Pause the video now to select the best answer. Okay, the answer is B, the general-purpose CPU. In process switching, the general-purpose CPU is responsible for making the forwarding decision, including doing lookups in the routing table and ARP table. Process switching is slow and demanding on the CPU, but these days it's still used for packets that CEF can't handle. The other components, TCAM, ASIC, and CAM, aren't used in process switching. Okay, let's go to question 3. Which CEF table stores layer 3 next hop information to enable high-speed forwarding? Pause the video now to select the best answer. Okay, the answer is A, the fib. The forwarding information base is built based on the routing table, also known as the RIB, and the fib is updated as the RIB is updated. The fib contains layer 3 next hop information to allow the router to rapidly forward packets. B, RIB, is the routing information base, another name for the routing table. It is used to build the FIB, but the RIB itself does not enable high-speed forwarding. And C, Adjacency Table, is the CEF equivalent of the ARP table. It is used to encapsulate packets with a proper Ethernet header. Okay, let's go to question 4. Examine R1's FIB. What action will R1 take for packets destined for 224.0.0.5? Pause the video now to select the best answer. Okay, the answer is B, receive. That's because 224.0.0.5's most specific match in the FIB is 224.0.0.0/24. Note that there is an entry to 224.0.0.0/4 above it, but just like in the routing table, the most specific match in the FIB is preferred. Okay, let's go to question 5. Examine the following adjacency table entries. What source and destination MAC addresses will be used when forwarding packets to nexthop 192.168.12.3? Pause the video now to think about the answer. Okay, the answer is D. The source and destination MAC addresses are indicated in the output I've highlighted here. Note that the order is destination, source, and then type. That's the same order as in the Ethernet header, so remember that. Okay, that's all for the quiz. Now let's check out a bonus question from Boson Software's ExSim for ENCOR. Okay, here's today's Boson ExSim practice question. You issue the show IPsef command on a Catalyst switch and receive the following output. Okay, so here is the output, and the question is, which of the following statements are correct? Okay, so there are 5 statements here. I want you to pause the video now and select the 2 correct answers. Okay, so hopefully you got those correct answers. Now let's check one by one. So I'll just go from A down to E. Okay, first A. 192.168.1.0/24 is a directly connected route in the routing table. Okay, so let's find that here in show IPsef. Here it is, 192.168.1.0/24. Next hop is attached. Okay, so I would say that A is correct. Directly connected routes in the routing table will show up with a next hop of attached in the FIB output of show IPsef. Okay, next B. IP routing is not enabled. Okay, so this is a switch. It's a layer 3 switch. I'd say IP routing is enabled because, well, it's using CEF to forward packets. Okay, C. All broadcast traffic will be discarded. Okay, so there are a few broadcast entries here. For example, this one at the bottom, 255.255.255.255, that has a next hop of receive. Receive packets will not be discarded. They will be received by the router. There are some other broadcast addresses. For example, this one here, 192.168.2.0/24 is attached. So that is a connected network to this switch. And this is the broadcast address of that subnet. And it has a next hop of receive also. So C is not correct. How about D? No default route has been defined. Okay, so this prefix here is for the default route. This entry is always in the FIB. It always shows up in show IPsef. But if there is no default route in the routing table, it will have a next hop of no route, as is the case here. So I think D is correct. No default route has been defined. As for E, the IP address of the VLAN 3 SVI is 192.168.2.2. Okay, so here is the entry, 2.2/32, and the next hop is attached. So I say that E is incorrect. Well, actually, we already know it is incorrect because we've already selected the 2 correct choices, but I'm checking it anyway. So attached means that it is directly connected, but it is not an IP address configured on the device. So a difference between the routing table and the FIB table is that in the FIB, when you have a layer 2 adjacency, meaning ARP has been completed, there's an entry in the ARP table, an entry in the adjacency table, that IP address will also appear in the FIB, in the output of show IPsef. So this address here, 192.168.2.2, is not the IP address of this switch. It's an IP address of another connected device. This one here, .2.1, the next hop is received, so I'd say this is the IP address of this switch's VLAN 3 SVI. And 2.2 is the IP address of another connected device, not this switch. Okay, so I will click on Show Answer, and indeed A and D are the correct choices. So here is Boson's explanation. I recommend pausing the video to read through it. And there are some references here, both to some Boson curriculum, to the official cert guide for ENCOR, as well as some Cisco documentation that I highly recommend reading. It's available free online. Okay, so that was a quick look at Boson Software's ExSim for ENCOR. I hope this video was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Yonatan Makara, Velva Jacob, George Streeter, Funny Dart, Nisir Chowdhury, Devin Suku, Gustavo BR, Gerard Baker, Marcel Lord, Pavel M, Mr. Erlison, Dragos Hernea, Zakib Shah, Mayor Salman, Mazen Anderson, Vitaus194, Gina Lindley, Nehemia, Justin Watke, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Ali Polat, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavus, Samuel Tavares, Mustafa Irsoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Gemajev, Ahmed Ismail, Dibia Swain, Tan No, Arlen Plagaria, Adelson Pereira, Abdo Zizo, Farad69, and Lucien Stoichitoyu. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.